Hi, everybody. This is our lesson in which we introduce hypothesis testing and talk about the z-test. That's Z as in Zorro. So this is the first section on hypothesis testing, and hypothesis testing is what we're going to be doing the whole rest of the semester. So it's very, very important that you get these ideas down, particularly the overall process and the language of hypothesis testing. Because, if you don't get these down now, it's going to come back to haunt you every single day, pretty much for the whole rest of the semester. So let's get started with an example. We're going to take a random sample of pizza deliveries from a company that says they deliver in less than 30 minutes on average. So we take a sample of 50, and they have a mean of 28 minutes, and we're going to assume that the population standard deviation is 5.6 minutes. And based on this sample, we want to know, is that enough evidence to suggest that the population mean, the mean of all of their delivery times, not just these 50, is less than 30 minutes? So this is the kind of question that we're going to be able to answer using hypothesis tests. And it's always going to be of the form, based on information in a sample, can we conclude some hypothesis about the population? So hypothesis testing is by far the most common tool used by statisticians, and it's going to be the whole rest of the course. Anytime you read a quantitative journal article, 99% of the time it's going to have a hypothesis test in it. So for every hypothesis test, there's two hypotheses. The first one is the null hypothesis, and it's labeled H with a 0. That's not a letter O, that's a 0. And we read that as H naught. Okay, it's not as in nothing. It's all for naught. The other one is called the alternative hypothesis, sometimes called the research hypothesis. And it's labeled either HA or H1. And different textbooks use HA versus H1. We'll sort of go back and forth between them, and there's no rhyme or reason as to which one we'll choose at a given moment. So it totally doesn't matter. You can use either one. So with these hypotheses, the alternative hypothesis is the one we're looking to prove. More about that word prove in just a minute. The null hypothesis is just what we have to assume unless or until we have enough evidence to conclude that the alternative hypothesis is true. So again, we're assuming H naught unless we have enough evidence to conclude HA or H1. So let's talk a little bit about the logic of hypothesis testing. So with the logic, we said that we want to demonstrate that the alternative hypothesis is true. So what we're doing is we're going to assume the opposite and show that the opposite is unlikely. So again, in order to show H1 is true, we're going to assume H naught and show that H naught isn't feasible. So hypothesis testing hasn't been around all that long. It's only been a little over 100 years. And it was modeled after the criminal justice system in the United States. That philosophy that a person is innocent until proven guilty. So that's where we get these hypotheses of HA, the alternative hypothesis, being the thing we're wanting to test, the thing we're trying to demonstrate, versus H naught being the thing that we have to assume unless we can find enough evidence in favor of the alternative hypothesis. All right, so we assume H naught unless or until we can show HA. So in this analogy, and this is getting into some of the very important language, there are two possible conclusions. If the jury finds that the defendant is guilty, the language that we would use is reject H naught. There is sufficient evidence to conclude that the defendant is guilty. There's always two parts to these conclusions. The first one is whether we reject H naught, and the second one is whether there's enough evidence to conclude the alternative hypothesis. So finding the person guilty means there's enough evidence that we can reject this null hypothesis, which means that we can conclude what we're looking to show in the alternative hypothesis. All right, so reject H naught, conclude whatever is in this alternative hypothesis, which in this case is that the person is guilty. Now, if the jury acquits the person, if they find them innocent, that does not actually mean that the defendant is innocent. And there have been examples, you've probably seen some in the news, where the jury said, we really didn't think the person was innocent, but they just didn't give us enough evidence to convict. So all that is to say that if we don't reject H naught, we don't say that as we conclude H naught, or we accept H naught, or we affirm H naught. The way we say that is we fail to reject H naught, which tells us that there is not sufficient evidence to conclude what we're looking to show in the alternative hypothesis. So again, just to give you a minute to think about that, and you can pause the video and think about that if you want to have some time to process that. If the person is found not guilty, we are not saying they're not guilty. We're just saying we've not been able to eliminate H naught as reasonable or as likely. So we fail to reject H naught, which means we cannot conclude what's in the alternative hypothesis. Now that sounds like a double negative, but it's really not. When we say we fail to reject H naught, what that really is telling us is that it's inconclusive, which is, I know, very unsatisfying, but that's the reality of it. So there's only these two possible conclusions. And I know I keep saying these, and that's on purpose, because I hope if I'm obnoxious enough in repeating it, that it'll sink in. So the two conclusions are reject H naught. There is sufficient evidence to conclude whatever we're looking to show in the alternative hypothesis, or fail to reject H naught. There is not sufficient evidence to conclude what's in the alternative hypothesis. Okay, there's no mixing and matching or anything. It's just reject H naught. There is enough evidence to conclude the alternative. Or fail to reject H naught. There is not sufficient evidence to conclude this alternative. So again, we never say we conclude H naught, or accept H naught, or affirm H naught, because that implies that that we have enough evidence to conclude the null hypothesis. And this is a common thing we talk about in statistics, so there's a ton of memes about this online, and I'll apologize in advance. I put a few of them in this presentation. I couldn't resist. And here's the first one. You do not accept a null hypothesis. Instead, you fail to reject the null hypothesis. And a word about this word proof. Even if we're able to conclude the alternative hypothesis, we still don't say that we've proved it. Proof means that we have incontrovertible evidence. We don't ever have 100% proof of anything in statistics. We always have to leave that room for doubt. So we just say, yeah, there's enough evidence to conclude the alternative hypothesis. We can't say we have proved the alternative hypothesis. All right, so the steps in hypothesis testing. Every hypothesis test we're going to do the whole rest of the semester has these 4 steps. And I know you don't know these terms yet, so we're going to go through and I'll explain what each one of these things mean. So the first thing you're going to do is you're going to set up your hypotheses. And the next thing you're going to do is you're going to calculate something called the test statistic and something else called the p-value. These, in the courtroom analogy, would be the evidence. The rejection rule is going to be, how do you know whether to reject H0 or not? In the courtroom analogy, that would be the standard of evidence, whether they're looking for proof beyond all reasonable doubt or something along those lines. And then finally, you're going to state the conclusion in the words of the problem. And I'll show you what all this means. But essentially, every hypothesis test follow these 4 steps. Set up the hypotheses, calculate your test statistic and p-value, state your rejection rule, and then state your conclusion. So now let's look at our first hypothesis test. So this is called the z-test for the mean, and we're going to be comparing the mean to a number. And that number that we're comparing the mean to is called mu naught. It's a mu with a subscript of 0. And we're going to actually have numbers in here, but these are 3 possible sets of hypotheses. We might want to show that the population mean is less than some hypothesized value, or we might want to show that the population mean is greater than some hypothesized value, or we might want to show that it's just not equal to some hypothesized value. For the null hypothesis, the opposite of not equal to is obviously equal to. So for this one, we're going to be assuming that mu is equal to the hypothesized value, unless we can find enough evidence to show that it's not equal to. Now, if you notice on these other 2, the null hypothesis, we have that written also as equal. Some textbooks will show you that the opposite of less than is greater than or equal to, and the opposite of greater than is less than or equal to. And that's fine if that's what you want to do. I'll show you a little bit more about that later, but really you're never going to conclude the null hypothesis anyway, so it doesn't really matter. I think it's easier to just go ahead and always have your null hypothesis be equal to. That way you don't have to think about it. So, by the way, this is a good time for me to mention the difference between what's called a one-tailed test versus a two-tailed test. And this is going to be important for us when we do stuff in SPSS. This test, where the alternative hypothesis is not equal to, is called a two-tailed test. And these other two are called one-tailed tests. And all you need to know about this is that it's a two-tailed test if the alternative hypothesis is not equal to. It's a one-tailed test if the alternative hypothesis is greater than or less than. And again, more about that in a minute. As we go through this lesson, I've been teaching statistics a long time, and what I've found is that people tend to do better if we explain how first and then get to the why. So in this lesson, we're going to do how all of it works, and you're just going to learn how to do it. And then we'll have a separate lesson where we get into why does it work. So for right now, you don't have to understand, why some of these things are what they are. We'll get into that. All right, so again, with the hypotheses, the alternative hypothesis is what we're trying to prove, and I should cross that out and say demonstrate, show, conclude. And the null hypothesis is what we just have to assume until we can show otherwise. So if a problem says a researcher believes the mean is more than 50, that means your alternative hypothesis is going to be mu greater than 50. And then the null hypothesis is then just going to be mu equals 50. These numbers will always be the same. And the only thing different between these two hypotheses is just the sign here. The null hypothesis is going to be equal to, whereas the alternative hypothesis is going to be greater than or less than or not equal to, depending on the problem. All right, so we're going to practice setting up some hypotheses. So in our first example, we want to know if the mean price of a flat screen TV has decreased since 2002. And in 2002, they're telling us it was $530. So in this case, the alternative hypothesis is what the economist wants to know. Has it decreased from $530? So the alternative hypothesis is going to be mu less than 530, which tells us that the null hypothesis is going to be mu equals 530. And I know I'm stating the alternative hypothesis first, but we always list the null hypothesis first. But you want to think about setting up the alternative hypothesis. So write down the null first, but set up the alternative first. So our second example. We want to know, does this tomato plant produce more than 20 tomatoes per season on average? So more than 20 is what we're hoping to demonstrate. So that means our alternative hypothesis is going to be mu greater than 20. And that means our null hypothesis is going to be mu equals 20. And finally, we want to know if the average sentence for repeat offending drunk drivers has changed since 1990 when it was 90 days. For this one, the word changed does not give us any indication of whether it's increased or decreased. So that means our alternative hypothesis is going to be not equal to. So mu not equal to 90 versus mu equal to 90. Okay, and again, this last test is a two-tailed test because the alternative hypothesis is not equal to. And these other two, because the alternative hypothesis is one direction, less than or greater than, that means those are one-tailed tests. So for our pizza delivery example, we're looking to show that mu is less than 30. So that means that's going to be our alternative hypothesis. And the null hypothesis is going to be that mu equals 30. So now that's it for setting up the hypotheses. So moving on to the second step of hypothesis testing, we're going to talk about how to calculate the test statistic. So all of the hypothesis tests that we're going to do, they all have a test statistic and a p-value. For the z-test, this is the formula for our test statistic. And if this looks familiar from the central limit theorem, it's because that's what's going on in the background here. So it's going to be x bar, so the sample mean, minus the hypothesized value, divided by the population standard deviation over the square root of the sample size. And I call that z star just to distinguish it from z, but your textbook just uses z, which is fine, but you'll see me use the z star. So for our pizza delivery example, we said that the company was claiming to deliver in under 30 minutes on average. We said that, so 50 then is going to be our sample size. So that's going to be m. We said 30 minutes was our hypothesized value. The sample has a mean of 28 minutes. So that's the sample mean, which is x bar. And the population standard deviation is sigma, which is 5.6. So for each one of these problems, you're going to need to be able to read the problem and pick out what's each one of those values. So that's why I've been harping all semester on, do you know those symbols? So if we just take all those values and plug them in, the sample mean minus the hypothesized value over the standard deviation over the square root of the sample size, we get negative 2.53. And I'm going to pop out of here and show you how to do that calculation. And I'm going to show it in Excel because I think most of you have calculators that work the same way. There's a couple different formats that calculators come in. So we need to put parentheses around the top so that the calculator knows the order of operations we need. And we're going to put parentheses around the bottom as well. And when we do that computation, we get negative 2.53. And you're going to want to round that to at least 2 decimal places. More is better too, or more is good too. But I would practice typing that in and make sure you're getting the same value that I am. So this is easy enough. It's just a matter of plug and chug. All right, so moving on to p-values. So the formula for calculating the p-value, there are 3 of them, and it's going to depend on what the direction is of your alternative hypothesis. If your alternative hypothesis is mu less than mu naught, then your p-value is going to be probability z is less than your test statistic. If your alternative hypothesis is greater than, this sign here is going to be greater than. If your alternative hypothesis is not equal to, then you have to find the absolute value of your test statistic. So In other words, if it's positive, you just leave it alone, but if it's negative, you just get rid of the negative sign. Find that probability that z is greater than that, and then multiply it by 2. All right, so let's do some examples. So let's suppose that we are doing a problem, and we've got these hypotheses and this test statistic. So in this problem, what matters here is that this alternative hypothesis, the sign is less than. Okay, so that means we're going to go up here and look for the one that says less than, and that's this one here. So our p-value is going to be the probability that z is less than the test statistic. Well, they're telling us that here we've got a test statistic of negative 1.34. So our p-value then is going to be probability z less than negative 1.34. And if we go over to StatCrunch, you know how to find that probability. It's just with a mean of 0 and a standard deviation of 1. Plug negative 1.34 inside the parentheses. Make sure it's less than. And that tells us that our p-value is 0.0901. Okay? And again, we use the less than formula because this direction was less than. Looking at example 2. Example 2, if we're doing an example where our alternative hypothesis is greater than, we're looking up here for greater than, and this tells us that our p-value formula is the probability that z is greater than the test statistic. So that means that our p-value is going to be probability z greater than 2.45, again, just this test statistic. And if we plug that into StatCrunch, greater than 2.45, we get a p-value of 0.0071. And like I said, I'll explain in a separate video what exactly p-values are telling us. For right now, we're just going to focus on how to do them. So for the third example, we've got an alternative hypothesis where the direction is not equal to. This one's the two-tailed test. And if we suppose our test statistic is negative 1.88, we're looking up here for whether for where the not equal to problem not equal to formula is. And this is the one where we have to take the absolute value. So the absolute value of negative 1.88 is going to be positive 1.88. So we have to find the probability that z is greater than 1.88 and then multiply that by 2. So the probability that z is greater than 1.88, we just point this to greater than 1.88. And we get 0.0301. Multiply that probability by 2, and we get 0.0602. This is the only one where you have to multiply by 2. And it is directly related to the fact that it's two-tailed. So for the example that we were working on with the pizza deliveries, we got a z-test statistic of negative 2.53. Our alternative hypothesis was less than. So less than means this is less than. So our p-value is going to be the probability that z is less than negative 2.53, which is going to give us a p-value of 0.0057. All right, so we're finished with the second step. The good thing is the third and the fourth steps out of the 4 are a lot quicker. So the third step is the rejection rule. So the rejection rule is just reject H0 if the p-value is less than some value called alpha. Alpha, which looks like a little fish, kind of looks like an A, but it's a Greek letter alpha, is called the level of significance. This is something that's set before the test starts. And if they ever don't specify, use 0.05. But the three common values of alpha are 0.1, 0.05, and 0.01. So the rejection rule is always 100% of the time, reject H0 if the p-value is less than alpha, less than the level of significance. And this is regardless of whether the alternative hypothesis is less than, greater than, or not equal to. And I'll explain why in that next video where we explain how all this, or why all this works the way it does. For now, I want you to pause the video and repeat this to yourself over and over and over again, about 5 times. And I don't care if you're in a public place and people look at you funny. Reject H0 if p-value is less than alpha, the level of significance. Okay? So anytime the p-value is less than alpha, that's when you're going to reject H0. Otherwise, you're going to fail to reject H0. And I'm a little bit of a nerd, so I had this stamp made. You can go online and have a stamp made. Because I feel like I say this so much. They wouldn't do a subscript though, so this looks like, it looks like reject ho, but reject H0. By the way, don't call those ho and ha. Okay, it's H0 and HA, or H1, it's not ho and ha. So anyway, reject H0 if the p-value is less than alpha. All right, so here's the results of my stamp. And if you'll get this wrong, I'm going to stamp myself in the forehead. Of course, I don't want to incentivize you to get that wrong. But reject H0 if p-value is less than alpha. And here's a couple of memes to maybe help drill that home. I don't always reject the null hypothesis, but when I do, it's because I found a small p-value. And also, is that Ryan Gosling? It's either Ryan Gosling or Ryan Gosling. I think it's Gosling. Anyway, you must be p greater than 0.05 because I fail to reject you. So we're rejecting H0 if your p-value is small, usually less than 0.05. And we're failing to reject H0 if the p-value is large, usually greater than 0.05. So for the example that we're doing with the pizza delivery, suppose we're going to use 0.05. Our rejection rule is then going to be reject H0 if the p-value is less than 0.05. So that's it for the third step. The fourth step is just stating our conclusion. The p-value we got was 0.0057, which is less than 0.05. Therefore, our conclusion is reject H0. There is sufficient evidence to conclude what that alternative hypothesis says, which is that the mean of all delivery times is less than 30 minutes. So they've supported the restaurant's claim. And by the way, I know I've been saying verbally, reject H0, there's sufficient evidence to conclude HA. But this is what I mean when I say you're going to write this in the words of the problem. You're not just going to say conclude HA. You're going to say that in what that actually means, that the mean of all delivery times is less than 30 minutes. All right, so that's one example. We're going to do another example in just a sec. But just to reiterate, and if you notice how many times I'm saying some of these things, it's because of how much I want you to remember them. 2 possible conclusions to a hypothesis test. Reject H0 which means there's sufficient evidence to conclude whatever the alternative hypothesis says, or fail to reject H0, there is not sufficient evidence to conclude the claim that you're looking to show in the alternative hypothesis. All right, so let's do another example, and we'll do it all the way from first step to last step all at one time. So in this example, we know that in the U.S., the mean weight of newborn babies is 7.4 pounds, and the standard deviation is 2.3 pounds. So for mothers who have gestational diabetes, we have 35 babies in the study and found that their average birth weight was 8.1 pounds. And we want to use alpha equals 0.01, or in other words, a 0.01 level of significance, to determine whether the average birth weight of babies whose mothers have gestational diabetes is higher than the national average of 7.4 pounds. So step one is going to be, we're going to set up our hypotheses. So our hypotheses are mu equals 7.4, the national average, versus mu greater than 7.4. And the way we know that this is the hypothesized value is they're saying, test whether the mean is greater than 7.4 pounds, the national average. So now we have to calculate our test statistic. So we have to figure out what these numbers represent in the problem. Well, the standard deviation of 2.3 pounds, that's going to be sigma. There are 35 babies in the study, so that's n. The average, the mean birth weight of those 35 babies, so that's going to be the sample mean, is 8.1. And then alpha is 0.01. So if we plug in over here, using the same process we did, we're just plugging in this for x bar. So we've got the sample mean minus the hypothesized value divided by the standard deviation over the square root of the sample size. When we do that, we get 1.80. That's our test statistic. Now to get our p-value, we're going to do, because this is greater than, we're going to do greater than 1.8, because that's our test statistic. And when we do that in StatCrunch, greater than 1.8, we get our p-value of 0.0359. So we've got our p-value now. The rejection rule, because they told us alpha is 0.01, is to reject H0 if the p-value is less than 0.01. It's not, therefore we're going to fail to reject H0. And since we fail to reject H0, that tells us there is not sufficient evidence to conclude what the alternative hypothesis says, which is that the mean of all mothers who have gestational diabetes, or the mean birth weight of those babies, is greater than 7.4, the national average. All right, so that's an example all the way through, and this is exactly how I want you to write it. You're going to start, because of just the logical progression of this is a logical argument here. We're starting with our assumption. So we're assuming that the mean is the same as the national average, unless we can say we're looking to see if it's greater than. Okay, so these are our hypotheses, and then here's our evidence. This is how we know what to conclude, and this is our conclusion. All right, so you want to put those in order, and I want you to show all of those steps. I'll mention that there are two ways to do a hypothesis test. We're going to use the p-value method because I think it's easier. It's also what's done kind of throughout, the real world. There's also something called the traditional method, which you may see in your textbook, and I wanted to mention it just in case you see it there. You could, instead of using the p-value to determine whether to reject H or not, you could figure out what the test statistic would have to be. But we're not going to do that. All right, so that's it. I hope you took good notes on this section. And if you have any questions, please let me know. Stay tuned for a video on why all this works the way it does.